So we initiated discussion on extended surface in the last lecture. So what it really means is that the amount of convective mode of heat transport is essentially given by the product of heat transport coefficient multiplied by the area of heat transport. So if I put a subscript S, it's basically the surface area of heat transport, because it's multi-phase system where the heat transport is from the solid to the fluid which is circulating around. So there has to be it's the surface area which is responsible for the heat transport via convection from the is flowing around. So if H is the heat transport coefficient, A is the surface area of convective mode of heat transport here, and delta T is the corresponding temperature difference. So this is essentially Newton's law of cooling. And we said that the purpose of any heat transport equipment or heat transport system is essentially to either increase the heat transfer rate if you want to dissipate the heat, or if you don't want to dissipate the heat, you want to cut down, you want to maintain the certain chamber with a certain temperature, then you want to cut down the amount of heat that is lost. So essentially it boils down to total amount of heat that is transferred from the system to its surroundings. So one way to increase, as we observed in the last lecture, is to increase the surface area of heat transport, and that is achieved by a set of systems, one class of system called the fins. So what we are going to see in today's lecture is we are going to look at what are the different ways of fins and how to understand heat transport process in these kinds of surfaces. So let us take a little general example. Okay. So we said that there is a base. Supposing if there is a so say it's a base solid. So note that the purpose is to increase the heat transfer rate to the fluid which is surrounding. So one way to do that is to have some sort of fins which are actually protruding out of these surfaces, and you could have many such fins, which are protruding out of these base surfaces, and there would be heat transfer from the top and the bottom surface of this fin, and of course in the sides also. So let us consider a generalized, an arbitrary shape, okay, fin, a general arbitrary shape. So let us assume that this is the varying cross sectional system, and we are going to take specific examples and specific cases of this generalized case, generalized fin. Extended surface. Okay. So if we want to quantify heat transport process in such a generalized system, we need to find the temperature distribution, and in order to find the temperature distribution, we need to write the energy balance. That's what we've been doing. So let's say we take a small element. So this is dx, and let this be the x direction, go to L, and let us assume that there is fluid which is flowing past this object everywhere at temperature T infinity. Okay. So there is some fluid which is flowing, and if I assume the steady state process, so let me make a few assumptions saying that it's a steady state, and let us assume that the heat transfer is primarily one dimensional, which means that the heat transfer is only in the x direction, and I assume that cross section temperature is uniform. So, I assume that every cross section the temperature is uniform, which means that the gradients are 0 in this cross section. Okay. But if the aspect ratio, that is if the radius of the cross section that we are considering, if that is substantially small compared to the length of the object that we are considering, then it is a reasonable assumption to make that the gradients in the cross section is negligible. If the aspect ratio is significant, if it is close to 1, certainly it is not correct to assume that the cross sectional temperature is uniform. There will be gradients in the cross section, and you will have to consider that, and that would require dimensional energy balance, which we will see a few lectures down the line. Okay, so what is the energy balance? So remember the mantra I told you in one of the lectures, whatever comes in this element, whatever leaves, plus whatever is generated inside the system or whatever is lost from that location should be equal to accumulation, right. So that is the mantra that we wrote. So input minus output plus generation equal to accumulation. Last term could be accounted in the generation by putting appropriate sign. So I will not write it as a separate term here. So supposing I draw the cross section, okay, so this is dx, that is dx, and A subscript c is the cross sectional area for conduction, and note that the cross sectional area could in principle be a function of the axial position. So this is in principle a function of x, okay, and the convective mode of heat transport is actually occurring from the curved surface area of this object. So along the curved surface area we see that there is a fluid which is flowing, and therefore there is constant heat exchange from the solid to the fluid along the curved surface area, and of course there will be heat transport from the end also. So note that the x equal to 0 basically corresponds to the, it is attached to the base, it is attached to the base equipment, so it is not exposed to the fluid, and there will be heat exchange from the curved surface and also from the lagging edge of the fin that we are considering, okay. So the, supposing I call dq convection is the differential amount of heat that is exchanged or that leaves this surface and is sent into the fluid stream, okay. So that is the amount of rate, differential rate at which heat is being exchanged. And if the amount of heat that, the rate at which heat is transferred to that element, input is qx, and if the rate at which it leaves is q of x plus dx, okay. So at steady state accumulation is 0, so therefore the balance is simply qx, which is the input, minus qx plus dx, which is the rate at which heat leaves this element, minus the amount of heat that is lost because of exchange of heat from the solid to the fluid which is flowing past it, okay. So minus dq convection, that is equal to 0, very simple. So whatever comes into that element qx minus whatever leaves, that is q of x plus dx, minus whatever is lost because of convection from the heat transport from the solid to the fluid which is flowing past that object, okay. So q, from Fourier's law we know that qx is minus k ac of x into dt by dx. So note that in principle the cross sectional area could be a function of the position, and so it is a variable cross sectional area problem. And similarly from Newton's law of cooling, dq convection is heat transport coefficient into dAs, and if the local temperature is T, multiplied by T minus T infinity. So that is dq convection. So, this comes from Fourier's law and this comes from Newton's law of cooling. So, when we substitute all this, minus K minus S into T minus T infinity equal to 0. Okay. Any questions on this so far? So, now I could rewrite this as d by dx K A of x dt by dx equal to d by dx h s into t minus t infinity. So, if I assume that the thermal conductivity and the heat transport coefficient are not function of position, then one could pull it out and say K d by dx A of x equal to h. Is t minus t infinity a function of position in this term here? Yes or no? But you have to watch out. So, this is the d by dx rate of change of convection, convective term, right. So, here what is changing? Is the area changing with dx or t minus t infinity? What should you consider? So, note that this is the differential balance, right. So, you are looking at what is changing in this small element. So, when we say Newton's law of cooling, we assume that the cross sectional temperature or the local temperature of that element is constant, and therefore, what is changing here with respect to convection from the solid to the fluid is the cross sectional area. So, therefore, we can rewrite this as dAs by dx into t minus t infinity. So, keep in mind that the what is changing here, the so in this small element, whenever you look at convective heat transport from the solid to the fluid along the cross sectional area, so in the differential balance, so note that this is very important assumption that you make in differential balance, that the local quantity that you are considering in the control volume, you assume that the local quantity, the element is small enough such that the local quantity remains constant in that element, and therefore the t minus t infinity in this small element must remain constant. It is not a function of dx. Excuse me? That is already accounted here in the gradient. So, the temperature change that you are seeing here is inside the solid. That variation is already accounted in the diffusion term. So, what causes the temperature variation inside is the conduction process. So, the variation of temperature inside the solid is already accounted for here. But when you are considering convection, what is causing convection? The driving force of convection is the local temperature inside the solid and the local temperature in the fluid outside. And the one previous to it, the left hand side and right hand side, they're not, are they mathematically correct? They are correct. But like, you could have some chain rule to account for the temperature variation in the right. That is correct. If you use the chain rule, so note that, look at dq here, this is the differential amount of heat that went in. This differential amount is because of the differential area and not because of the differential temperature gradient. So, if you use the chain rule, the differential temperature gradient is 0 because you assume that the temperature in the small element is same, and that is the basic assumption of any differential balance. In a control volume, you always assume that the temperature is constant, and therefore the differential amount of heat transfer that occurs because of convection is because of the differential amount of cross sectional area or surface area which is present. And therefore, even if you use chain rule, you could use, even if you use chain rule, in this term the differential temperature difference will be 0, because you by nature of the fundamental premise of differential balance is that the local temperature gradient is assumed to be constant. So if you use that property, then even if you use chain rule, that temperature gradient will be 0. Okay, so we can simply write this as k into AC of x. I should have put a subscript here. So AC of x into d square t by dx square plus k into dAc by dx that should be equal to h into t minus t infinity into dAs by dx. Okay. So note that in the conduction term, the gradient in the or the net heat transport rate is now going to be a function of both the temperature gradient and the cross sectional area gradient, unlike what you see in convection term, because the convection here occurs along the cross sectional area, and you assume that the driving force for convection is the local temperature gradient. So that is the key difference why this kind of why if you use a chain rule the temperature gradient will be 0. Okay. Any other questions? Okay. Alright, so this is the general balance. So we can simply rewrite this as d square t by dx square plus 1 by AC into dt by dx, that is equal to h into t minus t infinity divided by k into AC ds by dx. So this is the general balance for the arbitrary geometry that we had just considered. Okay. Any questions on this so far? Yes. AS is the curved surface area. Curved surface area of the object. Maybe you came late, you didn't see the exact picture. Yes. Okay, so let's draw the picture again. Supposing if this is the arbitrary fin, okay. So the conduction occurs in this direction. So this is the heat transfer rate because of conduction. Okay. So conduction occurs from, so this is the base of the object. So the fin is actually protruding from the base, and so the heat is now carried from the base to the fin, and there is conduction mode of heat transport which is carrying heat across. Okay. Now we have fluid which is actually flowing past this object on all directions. Okay. So now, so the heat is lost from every location in the curved surface. So at any location x, Ax is essentially the, supposing if the radius is given by, r, okay. So at any differential As, any location x, the differential area of conductive mode of heat transport is simply given by 2 pi r times dx, if the thickness is dA. So you cannot define, because you need a, see, for any heat transport to occur, you need a cross sectional area, correct? Now you need some cross sectional area at which the heat transport is going to occur, and so at any given location you need a definite thickness in order to define heat transport process. So supposing if I look at the, so this is the cross sectional area. Supposing if I know what is the total length, then I know what is the total surface area of heat transport. But if I want to know what is the heat transport at a given location where the cross sectional area is changing, then you have to define a specific thickness, otherwise area is not defined. So if you define a specific thickness, then that's the area that you have to consider. So definitely when you want to define an area of heat transport, you need two dimensions. You cannot define with just one dimension. Area is not defined. So you need two dimensions in order to define a cross-sectional area. So you need to define, if it is a varying cross section, then you need to have at least a small thickness at which the convective heat transport is going to occur. Now if it is non-varying cross section, that is if the cross section is same, then you could actually consider what is the overall area of heat transport. Is that clear to everyone? Any boundary condition, we are going to see that. So note that conduction is occurring in the x direction. So the whatever heat transport that is occurring in this boundary is accounted as a boundary condition. That's what we are going to see. It doesn't matter whether you do integral or the differential balance. In fact, we are going to see in a short while, in order to estimate some of the properties, there are many different ways to estimate properties. Whether you use the integral method or whether you use the overall maximal heat transport method, you are going to get exactly the same answer. So the differential and the integral balance can actually be merged together in some sense. There are formal ways to do that. So there is no need to worry about whether if I use integral balance will I get a different answer. You will not. You will get exactly the same answer whether you use an integral or differential balance. You are going to see that in a short while. That's the next case we are going to consider. And that's rightly pointed out. That's the obvious case that you would want to consider, right? That's the immediate thing you want to check, whether if we say cross sectional area is independent of the x direction, then what will be the case? So in the original energy balance equation, supposing you write multidimensional energy balance equation, okay? So let's take that for a moment. Let's digress for a couple of minutes. So in principle, you could derive the same equation from the generalized energy balance also. So the generalized energy balance is K del square T. So this is the generalized energy balance, right? Generalized energy balance is K del square T plus whatever is the amount of heat that is generated inside the solid, okay? And that should be equal to the accumulation term. So if you assume steady state, accumulation is 0, and if you assume that there is no heat generation inside, that's also 0, okay? So K del square T equal to 0 is your model. But keep in mind that the heat transport that is occurring from the curved surface is now going to appear as a boundary condition in the radial direction. So if I write the boundary condition at r equal to, let's say, capital R, which is a function of position x, then I'll be minus k dt by dr, that's equal to h into t minus t infinity. So that will appear now as a boundary condition. Now the way to get this model from here is, all you have to do is, you say that, so note that we did not include one of the assumptions. We said that the cross sectional temperature is uniform. So how do we incorporate that? So you integrate model equation with respect to R. If you integrate, just give me a second. If you integrate with respect to R, so keep in mind that you have to use the correct weights, okay? So note that you are now dealing with the radial coordinates. So you have to account for, when you integrate the radial coordinates, you will have to account for change in the cross sectional area. So the correct integral is essentially r dr, t times r dr, okay? So what you will get is a cross sectional averaged temperature, okay? So this T is essentially, we are assuming that the radial distribution is uniform, right? We said that there is no gradient in the radial direction, which is equivalent to saying that it's a cross sectionally average temperature quantity. So now if you integrate this equation in the r direction and substitute the corresponding boundary condition, you should get that. And in fact, it's a good exercise to check. So account for the varying cross sectional area and you incorporate this integration into your model equation and you will be able to get that. So this is the way to go from the generalized equation. In fact, we will not discuss this. So this sort of assumption is called lumping or averaging in engineering literature. So it's a very common technique used when you model different engineering systems. So you can use a lumping method if you know that the aspect ratio of a certain problem is very small. That is, I define aspect ratio as the radius divided by the length. If that is very small, then you could actually do what is called a lumping assumption and then you get a one-dimensional model.